Up for everybody. This new version is a little bit weird. Okay, so what I did was set my screen up here, and I just want to be sure that you guys can see my PowerPoint and you can hear me. Anybody want to chime in and let me know? I got a yes. All right, so it looks like we're there. Wonderful. So it's being recorded. Week 5. This lecture is going to be a little bit shorter. We can go longer if you need me to. I kind of been cranking on you guys a little bit in the lab and stuff, so maybe this lecture would be a little bit shorter. And the lab has potential for being a little bit shorter if you come prepared, and I'll talk to you about that in a minute. So I do attendance here. I can pass back papers when I see you guys. These get graded and collected. I saw there was 7 assignments in here. I graded some of them. I haven't graded 7 of them. Lab 4, I just touched base. Looks like people were done with that. That's good. If not, I guess Saturday morning you can come in and just tidy it up. But most people were getting close on the Ethernet IP. They didn't run through the device net. They were just trying to finalize the Ethernet IP. Yep, 9 a.m. Jeff, do you just have the Ethernet IP left? Is that correct? I thought you had it all done, actually. Or you just want to come in and get started on the next one? I'm done one part on 3. Okay. Yep. The next lab, if you do come in, everybody, it is a 3-phase lab. We're using a big grinder motor. So you can take a look at this lab and you can get started on it, but you're going to run out of things to do because I don't want you to hook up the 3-phase and everything until I get there. But what you can do is thoroughly review the lab and take a look at what you're going to have to do when you get there. And I'll reiterate here at the end that this can actually go pretty good in a couple of hours if you understand what you're doing. You looked at it ahead of time, you checked your IO, all this stuff, what you're doing in the ladder logic. Or we get people who kind of come in and they mess it up. And I'll give you a few little tricks here. And it just takes forever. They just don't even get it done because they got to start over like 2 times. Your choice. We'll review it, but prepare yourselves, and it could go. All right, good news or bad news? So that's good news and bad news. There's something really messed up in my lab paper. The lab, you can't see it, or you see that it's doesn't make sense the way that it's written. It should be also on the D2L if you need to download it. Or you can send me an email and I can send you something. Good news. You've spent a lot of time in the lab. That's good news. And you're getting much more familiar with the software. So we are. Some of the text is really wacky. I can't send it for you. It should be the lab on D2L. So if you go into the D2L, and that's what I'm going to be doing. I'm going to be going into the D2L and pulling up the lab. Hopefully you can take a look at that and download it and print it if it's messed up. But it should be under D2L. So once again, getting around the software pretty well, okay? Which is good because you spend a lot of time getting around it. The bad news is you're spending a lot of time in the lab. So that's where I got here. Are you prepared? Just be prepared for this one. This next lab will run well if you take a look at it. I promise, if you take a look and try and understand what's going on, it will go well for you. If you don't, it will not go well for you, okay? A couple things, we've been blinking a lot of lights, and you know, everybody's got a little bit of a different way, but I really encourage you to keep this simple, especially when we start blinking a lot of other things. And that's where I have a contact here that's maintained, you know, whether this is a selector switch or bit memory where you start, you know, you hit start and you bring on a bit called system bit, and that locks in memory system bit. You know, this could be system bit, and then turn on the light. Keep the light on, keep the field device on its own run. Don't put any timers, don't turn any timers on to turn the light on. Just, if it says turn the light on, whatever's maintained, turn the light on. And then have the blink timer turn it off, and have the blink timer start the next run, which is the reset timer. which opens it up and it resets and it cascades. Now, use an alias. Here I'm just using the done bit. I could make an alias called blink timer done and then alias to the data blink timer.dn. It's up to you. That using the done bit was probably okay instead of using an alias. This is referenced in your textbook. You've got your old programs. Hopefully you saved them. So this has got to be the simplest way that I can think of to blink a light. If you understand the maintain contact here. Scale of 1 to 10, do you understand my maintain situation here? And then my circuit here, scale of 1 to 10, do you feel good about this? I hope so, because people are using timer timings and EN bits and, all kinds of stuff. I'm like, man, you're going to get yourself in trouble here if you just don't keep this simple, all right? And then the start here, and I know I'm, overkilling because some of you I didn't have, that start could just be the system. And that could be where you had, your safety relay, your stop, then you had your start, and then you had your system bit, and then that comes on. And a lot of times we'll throw an overload in here because all these are normally closed, and so they're all true. And so hitting any of these would bring down the system bit, and that system bit runs, all the logic in here. So that's kind of the simplest version of a state manager. If you guys end up taking PLC 3, we do a lot with state machines and state managers in that, okay? So that's just a little bit of a review from where we're at. AB documents. I gave you a bunch of Allen Bradley documents, and you can save these or you can pitch them, or next time you need them, you can go and look them up yourself. You may want to save some of these if you're ever using DeviceNet, Ethernet IP, stuff like this, because it's kind of a quick refresher of how to do it. Remember, these are just examples. It's not the same hardware that we have. I'm going to make fun of some people here in a minute. And he says, what are you going to do when you have to download procedure that in the hardware isn't, exactly what we're doing? You got to take a look at them and you got to improvise. I mean, if you were to Google Allen Bradley Control Logics PDF, if you were looking for something, you are going to get tens, if not hundreds, thousands of pages of documents with hundreds of thousands of pages. And you have to go down and find what you want and search it. And then in that 500-page document, find the item that you want. You do it all day, every day. Especially with the smartphones, it's great that you can just do that. But you gotta get good at it. So the AB generic documents, this is what it was showing, I think, in the AB generic. And so when you're going through this and you're setting up an IP address of 1088.72, you're not going to get very far, because we're using a 192.168.1 network, and then we need our own network in here. And this is showing a 5-slot chassis, with IO adapters and all this kind of stuff. So people do this. They go right through this lab and they set all this up just like this. And they come, Sean, where's the pressure switch, Sean? I don't know. We don't have one. We're not using a pressure switch. You gotta improvise here. So hopefully, I know this makes sense, but when you read the lab and the procedures, I'm not scolded. It's not 110 anymore. We just, read the stuff and hook it up. We're doing pretty good, but don't get tripped up on the documentation. Anybody use a lot of documentation at their work? Allen Bradley documentation at their work, for example? Corey says, yeah. Yeah, I mean, it's nonstop. That's all you do. You run into a problem and, you want to solve it. You're going to get on your phone and find the document and download it and start looking for the solution, okay? Here's the IO connections for the 1791.8 PBP. The wiring's here. If you got to hook it up, notice it gets DC voltage and then it gets ground. So it's plus and minus voltage. The inputs are sunk, which means that, you run the input and then it's got to go back to plus. And the outputs are sourced, which means, they go back to ground. And so it's very similar to what we've been doing by hooking this up. But people aren't reading this, and they're jumping the voltage here and jumping the voltage here, and then what you're doing is you're shorting out the IO block. Now we're fortunate because the DC on your trainer, is just a small DC power supply, and so what it does, it's got a thermal protection in it, and it shuts down the DC on that trainer, and which means it shuts down your managed switch. So the trainer's still on, but you don't realize that the DC went down, your IO block's down, your switch is down, and all of a sudden you spend like half an hour trying to get communications again. Really, what you got to do is unhook all the devices, let the DC power supply reset, cycle the power on it, and then boom, the DC comes back on, and then you can try it again. But if you hook this all up again and just do a dead short to DC to ground, you're just going to trip it again. Okay, so once again, I could ask, I don't know scale of 1 to 10, but I'm encouraging you just pay attention to the wiring on this. Use a multimeter if you have to try and figure out how it goes. Because by the time you call me over and say, Sean, this isn't working, I look at it and I look for about a couple minutes. I'm like, oh, you don't have any DC power. Then I know what you did. Lab was remote IO. It was a little bit of a patience. We had a few restarts. So remember, if Logix is freaking out on you and it's not doing what you want it to do, you might just have to save Logix, shut it down, restart, open it back up and download it, and boom, all of a sudden something works. I think quite a few people have done that and it works. You might have to restart your whole computer, I don't know, but especially when you're doing all these networks and stuff like that, sometimes you just got to restart everything. But it required a little bit of patience. We did all right. Still problems making a few connections. Read those wiring diagrams. So I figured part A was a Logix scan of about 40 minutes. Input mapping was quick, 20 minutes. And then hopefully the device on the Ethernet you set up in 60 minutes. So I thought this was looking like about a 3-hour lab. And some people get through it quicker than others, depending on, how prepared you were for it. Input mapping. So from now on, I want you to create an input map subroutine for all the programs. So if you're using IO, you want to put those into an input map. And it would be remote IO and local IO. You need to create an output map. Well, typically, you only have one output. All right, I'm going to tell you this. You only have one push button on the input, but you might be using that contact multiple times. On your output, you only have one light, but you only are going to have that programmed as once. So whether that output gets written, and then the scans don't hit right or not, it might not be as critical. Whereas if the input, as we showed you, if the scans hit at a different time and you've used the input symbol more than once, you can get a condition where the input is reading as true on one rung and false on the other. So the input mapping might be more important than having an output map sub. So if I explain that scale of 1 to 10 initially, did that make sense to you? Input mapping might be more important than output mapping. How do you feel about that? 10s? 10? Anybody else? You guys still with me? I know I'm talking kind of slow today. Because it seems like input mapping. Okay. Here's the deal though. If I map the output, all right. So let's say I had something here and I had light 1 and this was output, 2, 1. Okay. If for some reason I did map this light into a bit, then you're going to have a sub somewhere that's going to have this, output 2, 1 is really just going to be, a bit called light, so now all of a sudden, light 1 is fictional again. Okay. So here, if I did this and then I use, output 2/1, and I'm using it as a contact in there, it's getting to be fuzzier if it's going to get written at the same time, because this is going to be on the IO scan. All the ladder logic's going to be on the ladder scan. So, you think this and this are getting updated at the same time because it's the same address. But if I'm going like this and I have output 2/1 here, well, then I got the same thing where I could have both of these lights on at the same time, even though they're interlocked. So maybe you would want to map the outputs as well. Okay. And so when we were mapping the inputs, I just want to be sure everybody understood that, to be sure how that worked. And I'll explain it just one more time. What we did is we took the input, which is I1, I don't know, I'm just going to take some inputs here, I13, whatever. And we call this 1 PB, and let's say this 2 PB. So these get scanned and updated on their own separate scan. The ladder logic here is running a different scan. They are not synchronized. They are not running 20 milliseconds together. They could be running at different scan rates. But as soon as I take this right here, that is its own scan and is getting updated, it means that these bits right here, because these are no longer, these are just tags, they're just bits. These get created immediately during the input scan, and so now all these exist fictionally as soon as the input scan is complete. I've got all these fictional bits, and then when I write my ladder logic, I'm going to come here and I say, now I got 1 PB turning on, light 1. Well, this is fictional. This scan is fictional. This output is fictional. I took the inputs and I synced them or synchronized them up to the same scan rate as the ladder logic scan because these bits are fictional. So that was what we learned. Scale of 1 to 10. How do you feel about mapping the inputs to sync up the scans, I guess? Yeah, okay. And sometimes people don't do it. And I remember, when I've had students come in there and they'll say, I didn't know we had to do that. And they'll come in with a story like, man, this motor freaked out on us, something, this and that. And we looked at the ladder and we like, okay, maybe this weird situation happened. And what we did is we mapped the inputs so that it, stuff couldn't be true and false at the same time. And then it works fine. So it does happen out there, okay? So you got to map your IO. A couple of things on the communications, because that's what the lab was about, communications. Remember, RS Logic uses 500, used that USB to COM port. That was DF1 RS232 and the VH45 UIC. My current 260 crop is struggling with that, just like you might have done initially, but we're not doing that. Control logic, the 5000 we're using, generally uses USB to Ethernet adapters. It also uses USB A to B. I do a lot of that as well. And so when I take a look at a controller, your controller would look like this. The newer controllers got a USB A to B, and the newer controllers also have the Ethernet built right into them, so they can do some bridging here. Okay, but ours doesn't have this. We have a separate Ethernet bridge, which it's a EN2. It's got a 2-port bridge. Okay, and so I think the documents were asking for a 1-port bridge, but if you went online discovery and discovered your bridge, it would have come up as a 2-port bridge. So I just want to be sure you agree with that you could go online and discover your modules and discover the correct bridge, 1-port, 2-port, or 3-port, so that it would work. Scale of 1 to 10, you feel good about discovering modules online so that your program is going to work like you want it to work. Yeah, okay, good. You can't online discover that remote Ethernet. So I do, as I said, I do a lot of eBay, and so I flash a lot of eBay processors. And the eBay processors, the older ones that have a DF1, is great because I can get right into those. Not a problem with DF1 because I know how to use RS links, set it up my COM port, hit auto configure. If they have A to B on them, bang, I'm in business because I can hack right into them there. Because as soon as you plug these in, RS Link shows you what the Ethernet address on them is. My problem is when I buy a processor that does not have a DF1 or does not have a USB A to B, it's only an Ethernet processor. If somebody set that processor to an IP address, I have no idea what it is. You cannot look, because you have to set your USB to Ethernet adapter to your network, and then you have to look at a processor on the same network, and that's the only way you can look at the processor. So when I buy processors that are just straight USB to Ether or Ethernet processors, sometimes I get my butt kicked a little bit by those. All right. DeviceNet uses a bus network, okay, and Ethernet IP used the star network, and we did both of those, okay. The quiz is over some of this networking stuff, and it was pretty much just straight out of the textbook and the questions that you answered. Device net, 2 wires for power, 2 wires for communication, 3 different baud rates, 64 nodes, 0 to 63, and it's really slow on a SLC 500, but it was pretty fast on this. When we went through it, you could just stop once you started scanning. A couple things. There's different baud rates for device net. You have to be sure that you have your baud rates set correctly for your devices and your scanner, because if it's not looking at the same rate, or it's not scanning at the same rate as some of the stuff that's set up, it won't see it. Okay, so when you start getting a lot of remote IO, like robot scanners and stuff like that, and you want to set up, you got to be sure everything is running at the same baud rate or at the same scan rate, so stuff sees each other. And if you take PLC 3, we will do a lot where you have to do time synchronization and all this kind of stuff, so everything's is scanning on the same clock. RS networks, you set up your communication path either through the SLC 500 or the Ethernet. On the CLX, we used Ethernet. That's why it was so fast. We're using Ethernet controllers, and RS networks worked through the Ethernet because we saw it on our computer. Our computer is connected to our controller using Ethernet. So yeah, RS networks works through the Ethernet, even though that device net is not Ethernet. So does everybody agree with me there that device net is not Ethernet, but we could use Ethernet to look at it because we have Ethernet controllers? Scale of 1 to 10, do you agree with that? You understand that the two are working together, everybody? Anybody else? Okay, yeah. So we went online and we could upload the device, modify the module by double clicking on it. You had to set the scan list, and some people had some corrupt scan lists, so we had to go in there and delete them. I used to go in there and just delete the scan list in case something was on there from prior. You mapped the IO, and then you downloaded it back to the scanner. Now, and then it's saved. Once you get it in there and you got your Logix programming going, you could just walk away and you could take your computer with you. You don't need RS networks anymore. It's set up, it's working. You cycle the power on the PLC, boom, your device net's working, your program's working, everything is working fine. So it keeps track of everything once you download the program. So when you talk about device net, it's still out there. I don't want you to go out and tell your boss that, hey, we need to set up a device net network. Don't do that, because it really is pretty obsolete. Ethernet IP is a lot better, okay? So that was, your device net. And the device net data table needs that enable bit set to 1. And so, it can be done via the data table, or you could just, put a selector switch in there and then toggle it over. So I think everybody felt pretty good about this. Let me do this on mine. Let me see if I did it on mine. I didn't. But what I have is a device net here. My device net is on 5 down here. Okay. So once I put in IO, I get globally scoped controller tags. So if I come up, oh, I didn't want that. I want my controller tags. Get up there. Where'd it go? Get up there. Hey. Give it to me. Okay. Here's my 5 right here, right? On my local 5 outs. There's my command register right there, right? And here's my command register run. And when you have your global tags here, what you can do is you can just, highlight them. If you're not sure of your address, you could just highlight this right here. And then you can, Control C to copy it, should work. And then if you wanted, a selector switch to turn that on, you could come here. What's this? Control V will take it. Command register run, and so a selector switch would do that. But that's the best way to do your tags. Just kind of cut and paste if you don't think you can find them by drilling down into the data. Okay. So need to be set to 1. Address can be really confusing here. What's this one showing here? This is showing on my remote IO. Let me take a look at my device net again a little bit. But I come back to my controller tags. So here's my command register, right? And here is my. I'm gonna get to there. Go. I'm gonna go to my data, and notice here that I got local 50 data 0, and it's a dint, which means inside of here I got 32 points or 32 bits on this data point. 32. And how many do I have? I got 32. And if I were to scroll down here, and this is kind of in my way, if I can get this figured out. If I were to scroll, I've shown you, look at this, scrolling down, 32 times 122. 32 times 122. That's how many bits of data that I can bring in on this device net card, and that's a lot of data bits. And if you want local output 5 data 111.19, that's, you might just want to go here and hit Control Copy, and then go back to your main routine. And then, like I said, you can come here and Control Paste it, and that way you know what it is. Now, remember, if you were, let's say we're doing this with our inputs, you know, and you got to map your inputs, right? So that's the same thing. You're going to take this data point, and you're going, whatever it is in here, and you're going to take this and you're going to map it to, it's going to be input to a bit. So this confusing tag right here is going to be mapped to 1 PB. Okay, and then 1 PB is now part of the ladder scan. So scale of 1 to 10, do you fully agree that I can take this crazy looking thing right here and go into my input mapping sub and make it 1 PB? And then I can just use 1 PB in my program. Okay, so now you're like, man, that's a lot of mapping. There's 132 times 32 or whatever, 123 times 32. That's a lot of mapping. Well, there's different ways to do this with copy and synchronous copy. You could write subroutines to do it, you know, stuff like this that you could just import every time, or add on instructions. If you take PLC2, we'll talk about a little more better ways to map this. Okay, to go back to my controller tags here, when you, where is this thing? You know, I've got, let me see what I got here. I do have local outputs and I do have local inputs on here, just like yours. So is anybody using a template that they just do, you know, file save as and then pull it open, lab 5, lab 6, anything like that? Okay. If you are, that's a good idea. And then you just start programming, you know, no tags or anything in there. It's just there. Well, guess what? If you're using a template where you went online and you discovered modules, disabled the keying, had everything just working great, then boom, you're in business right away to start programming. Well, why don't you do this, everybody? Why don't, on that generic one on your main program here, why don't you make a subroutine called input mapping, and go ahead and map all your inputs. And you want to output map, go ahead and map all your outputs. That way, when you pull it up, the first thing you do, whether you're using them all or not, you have all your inputs mapped and all your outputs mapped, and then you don't have to do it every time. If you don't do it, every time you start a program for me, you're going to have to map your inputs and outputs by creating an input mapping sub, because inputs got to be mapped from here on out. It's up to you, but you might want to throw that into your template. Okay. Going to here. This was my controller tags. Once again, we're getting into our controller tags. I'm going to look at the Ethernet IP just a little bit, maybe jumping ahead. So what I have down here is my Ethernet IP. Here's my bridge. I put my bridge in right here, and underneath my bridge, I added the AENTR, and there's AENTs, whatever. I don't know that the literature had you added an AENTR, did it? It might have had you added an AENT. Well, there's a difference between the T. It's got 1 port, and the TR's got 2 ports. Yours has 2 ports. So you did have to look at the model number and add that. And then you were adding a 3-point chassis, similar to your rack. The 0 slot is the scanner or the point IO, and then we had Ethernet outputs and Ethernet inputs, and so we had a 3-slot chassis. Now, as you move forward with this, if you get into a problem, you can launch this AENTR. Let me pull up the properties. While you're online, assuming you got it to set to 3 compatible module, I haven't downloaded this, but I would disable keying. I have my network set up for what it was. But while you're online, you can go to chassis size here. I'm not online, and it might say chassis size for module in general might be different, and that means the module did not get set with the chassis size when you download. So you might have to you might have to click this set chassis size in module, and then boom, it'll sync up your module. Whether you had you thought you had 3 slots or 4 slots or 5 slots, we had 3. And then over here where this was all yellow, bang, it's hot and everything's happy. And then once you're all happy, you have controller tags right here, and then you're in business. You're just writing a program then. So scale of 1 to 10, that you think you can set this up without yellow over here. In worst case, you have to set the chassis size in the module, and you got tags, and then you're just programming like you normally do, mapping your inputs. So Ethernet IP, scale of 1 to 10. Yeah, gotta do a little more practice with it, don't you? What else? Ethernet IP, you guys feel okay about it? Scale of 1 to 10? All right. It's really slick. You're gonna want to mess with it and like it, because that's what you're gonna use these days. You don't want to use DeviceNet, you want to use Ethernet IP. And so a couple of other things. We did not have to set those. So the modules that we had a number on them, on that pinwheel, like they're set to 90 or 65 or whatever. You could set those all the way up to 255, right? But those modules go to 999. If you set that module to 999, you can enable DHCP, and you could assign it an IP address, okay? And so the reason, I want you to be sure you understand this, so you can move forward in life and be successful in life. If you're going to be successful in life, you got to understand this. Allen Bradley equipment, when you buy it, if it's going to come from the factory like that, a lot of times it's going to be on this network right here, okay? And if we were to click the thumb wheel to 70 on that remote Ethernet adapter, it would be 70. That would be my remote Ethernet adapter. The problem is that's just one network. There's a lot of people that use a lot of other networks. As a matter of fact, I just showed you a minute ago where they were setting something up, and it was on a 10.88.70.2 network. Well, that is not a standard factory default network for Allen Bradley, okay? And so if you do want, let me write that down, 10.88.70. something, if you want this to be your network, well, then what you got to do is you got to set that pinwheel to 999, or you could go into your bridge. Your bridge has got little pinwheels to set all the stuff, or you could go in and set it using USA to B, whatever. And then you could give it this network here, and then you could give this a number 13, and your controller could be number 14, and your partner's computer could be number 15. But there's a lot of different networks here that you might not, it might not just be this nice, okay? So can you picture this on a scale of 1 to 10, that when you walk up to a piece of automated equipment, it might not be this nice 192, it might not be a Class C network, it could be a Class B or Class A network. Everybody can see, you feel good, you don't know. I mean, it's whatever your company likes, okay, of what the network is. So just real quickly, does any, yeah, Corey says often, does anybody at work use different networks like this? Are you guys using 192 networks, or you're using 10 dot networks, or 127 networks? It's that first number. 127 is a popular network. 127. So that thumb wheel can get you into, depends on the age of machine. Jeff uses a 10.16 network, super popular. 10.16. Blah 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 blah. Super popular network. That Allen Bradley equipment out of the box is not going to work well with that. You are going to have to go in and set the network to 10.16 to dot whatever so that you can use it. Okay. So how do you do that? Well, what you can do is if you get something out of the box, it's going to be set to DHCP. If you go to 999 and set it to those weird safety cards fun, it does, yeah. That's a whole different deal. We'll talk about that in a minute. We'll talk about that in PLC3. You know, it could be set to DHCP. Now that's not a static protocol, that is the dynamic protocol, okay? And so if you have a piece of equipment that hasn't been set up, it's going to be set, it can be set to dynamic. And the way you do that is use a program called boot P. So I'm going to launch boot P. It's my DHCP tool. And the first thing it asks is, how do you want to connect? Or how do you want to look for this equipment? And I've got all this stuff here. I'm just going to click this right here. And it's not going to do anything. It says it's set in a 192.168.1 network. That would be where I'd be looking for this at. But I'm not really connected up to anything like that. But if I had set that to DHCP and I was looking for a DHCP thing, it would start populating everything here that is trying to talk to my computer over the NIC, the network interface card. And my, you know, some computers use USB to Ethernet adapters, some have USB ports and whatever, and it would start popping up here. And when I found it would show the MAC address actually. And so when it found the MAC address, it would come here. I could click it and I could say, assign this an IP address. And like Jeff said, if it was your network was a 10.16.1 network, then you would assign it here. Has anybody used boot P IP commissioning tool before for something that comes out of the box dynamic? This is what you would, this is how you could do it. It is not fun, okay? If you have to do boot, you had to do it twice. If you have to use boot P, if you have to use the boot P, what I recommend is unplug unplug the Ethernet from your computer and just plug that device directly into your computer. So when it starts looking for anything on the network, the only thing that it could possibly find was the item that you want to set the IP address on, okay? And then you can set the IP address. But if you plug it in the network and it finds like 50 things, then you're like, I don't know which one this is. And then what you have to do is you have to go look for the MAC address. And remember, we talked about that in 111 and in 260, that any device that you have right here is going to have a MAC address on it. Now this one not have it written on it. This has got a MAC address, although my eyes are pretty, I can't see because of my eyes. It's going to be on here somewhere, but this has, it's like a VIN number. If it connects to the Ethernet that has a MAC address, then you'd have to see the MAC address of this, match it up and assign it. Now, that's boot P. But this has a USA to B on it. So it's just plug and play. I can plug this in. It'll be set to DHCP. I can go to links. I can say links, change this to static, 192.168.1.55. Bang, I'm done. It's just so much nicer when you have a USA to B, so you don't have to use boot P, all right? When we hit the capstone, we get some problems. You might have to use boot P, and we'll do it, all right? Then you cycle power. Two of the same IP addresses do not work. Hopefully we'll get an example in class. We went over this, the IO and the children. You install the bridge first. I recommend discovery so that it will discover it and it will bring in the correct bridge. The bridges are pretty advanced. So when you start looking and you find this bridge right here, ENT2T, you have a TR, by the way. Notice I've got my IP address set. And this is, I'm running on version 24. I got a little program up here on version 24. You're using 28. So if you were to try and bring in one of the new bridges, like EN3TR or 2TR, this thing would freak out. It would say, because it doesn't know what it is. It's too new. The software came out before that bridge came out and was offered to the public. Okay. But my computer works really good with this stuff because I have version 37 on my computer and 36 and 35 and 34 all the way down to 21. Um, and so when I try to install a bridge ENT 3TR or 4TR, my computer knows what it is. Yours might not, depending on how high of a software revision that you have. Okay. Fortunately, the computers at school also have 37 on them. So when you installed it, it came in and it knew what it was. It did discovery and it found it. But these were the properties that you set in it. Notice, you got RS network server you want. There was my port configuration if you wanted to go and change some of this stuff. Disable keying, obviously. But I recommend online discovery. And like I said, you might even want to, from now on, put that in your template. Okay. We did that. We installed that under the Ethernet. We installed our children, and it looked like this. You might have to match the chassis here on the ENT2TR, and then bang, everything. You got tags. You got controller tags, and you can find it. Remote IO had to have a matching slot, so we didn't have any problems with this. I usually have that. It's like, let me look at mine. Let me look at mine. Here it is. Hang on. Here it is right here. I got outputs were first and inputs were in the second slot, because remember the 0 slot was thing. People go in and they set slot 1 as their inputs and slot 2 as their outputs. Well, it's not going to work. Just like on your local rack, it's not going to work either. So that, you just got to be sure that you got the right numbers down. Your children were added to a slot. What revision? What firmware? Once you're dialed in and it's working well, remember you can always go to RS links, and if RS links sees it, RS links tells you what revision and stuff all this is, and that can be helpful if you want to throw that in just to be sure there's not any issues. Scale of 1 to 10 there. Are you comfortable going in RS links and saying, hey, my input module is revision 3.012, and then I can use that? Are you guys using RS links to see what revision level stuff is? Yeah, good. But remember, if you discover modules online, it pulls in the revision, so you don't even have to look, and then just save it as your template. Okay. Addressing is more complicated. Input modules are not output modules, so that's another thing. We're doing a good job with this. But when you put this in, local 0 is my outputs, but I got local 0 I's and local 0 O's, and because of the way that the data it's not pre-configured, it's configurable, and so people get in here mixing up, what's the inputs and outputs. Local 5, that was my device net. Well, that has inputs and outputs, so that's what you got. My remote IO, once again, you're coming in, you got slot 1 that we said was my outputs, but slot 1's got a :I and a :O. So you just be sure that when you're picking data, you are drilling down and trying to get this point here, not an input versus an output versus input, depending on what you want. I think we're doing better with that. Certainly better. Once again, here's another thing. If you just can't get this to work because you messed it up, I think Nicola had put in a 4 slot or something. We were trying to get a 4 slot work. Delete it, man. Take it out of there. Start over, because sometimes when you get this set up, it's a mess. So just delete, start over. Always go to Logix. Even to hit save, kill Logix, restart Logix, and then try and add it again. Like I said, you might have to match the rack when you're online. I showed you how to do that. So in summary, the lab was involved. You basically succeed and get a variety of different devices to communicate all at once. A push button on device net could turn on something on Ethernet and then shut it off on the main rack. So you could get IO wherever you want. In remote racks, that's what you're going to see all over, because if you have a machine, 30 feet over there, you're just going to run an Ethernet cable over to a remote Ethernet IP adapter and plug your inputs and outputs there, and then have the Ethernet kick it back. You don't want to have to install a complete rack, right? Homework solution. So this homework solution, I'm taking a look at them, but once again, this is using a pressure switch, but you could think about this as surge for flow or something, that basically when this shuts and then we get power, all the way through here, the control relay comes on, which is going to then shut this, turn this on the motor. All these are going to come on, and then this is going to open. So we're going to kind of kill our rung here, or sorry, this is going to close right here. So that if this is agitated back and forth, let's say like on a flow or something where it's opening and closing while the process is going on, we're not continually resetting the system. Okay, so that was kind of the gist of this. And then it kind of locks it. It kind of runs for a minute, 1 minute here, and then boom, that pops open, killing all the memory. And then hopefully after a minute, any type of backflow or preventer, check valves or pressure or anything like that is all stabilized, and then we're ready to run this again when we need to. Okay, and then after 2 minutes, so it's after 2 minutes when this one resets, then your system can run again. Okay, so it's 1 minute to kind of converge on a solution, and everybody's happy, and there's no jumping around of my sensor here. And then after 2 minutes, everything's kind of primed again. So when I was looking at this, I see that, this situation right here, these two contacts together, that's just like a timer timing bit. So I recommended using timer timing. So when people did this for me, they just took this logic here and they wrote control relay and M, and I'm like, we don't use control relays anymore. And even using just bits and stuff like this, it doesn't exactly work like you want it to. Okay, and that's kind of the moral of the story. And you start saying here, oh, I got my off delay timer here, and my pump motor is my latch. Can I get rid of that? And so if you start looking at the way some of these work, it almost looks like it would work. But what I did do here, but it won't, is this seems to work right here, is I did put all my outputs here in series. Okay, a couple of other thoughts on this. This contact right here, this M contact, it probably should be a monitoring contact. So where I have a pump motor right here, I could have put, I would have to figure out some way, if I did want to monitor this, to put the auxiliary contact, and I just couldn't put it here because now I've got a problem that my pump would never turn on because my contact would never close. So it does get more complicated if you want to do something like that. And so that's just one little thing about this. If you're reading this, does that matter? Can I cheat doing logic? You can, but it might not exactly work like what you want it to. Okay, and so when we talk about converting ladder logic, and we say why, well, there's a lot of stuff out there that is run on relays, and it's worked for a long time, but you might want to upgrade it and put a PLC on it. So that certainly happens. When PLCs first came out, that was basically what they did. They started swapping out all these relays and replacing them with PLCs. All this ladder logic going away, PLCs there. Well, nowadays, we don't, I mean, it's still, you do it, but nowadays when you're designing an installation, you'll design it around the PLC, and you'll buy your field devices to match the PLC program and everything like that to be sure that it works. But there is still stuff where you would want to convert it and update it to a PLC. So has anybody done that before, where you took an old machine and you converted it over to a PLC by chance? Okay, well, it's sadly, yeah, it's like, oh, I just put a PLC on that thing, will work great. No, it won't. It's like, yeah, I had PLCs at LCC. I'm just going to take this thing right here that's all ladder logic, and I'm just going to make it work on a PLC. Man, it's crazy to just to look at the way some of this stuff works, and then when you put it into PLC, to just scratch your head and say, yeah, that's not going to work. This isn't going to work like it said it should. And there's ways to cheat around it, and it still doesn't quite work, or doesn't work, or there's extra stuff here. So you might do it. It's actually, there's a lot of system integrators that make a lot of money, updating this stuff. Okay, and that's what the thing is. Quiz review, real quickly on the quiz, and I said, like, this is going to be pretty fast. The MCR instruction establishes a zone and user with all can be turned off simultaneously. So we went over the MCR. It's almost like killing everything. Assume the MCR makes false to true. The result all outputs will be controlled by the respective input conditions if the MCR goes false to, would be false to do, so we're either jumping over it or not. The main advantage of jump to label is the ability to reduce the processor scan time. We said, well, these processes are pretty fast these days. I don't know if you need to jump over it, but hey, it could. The jump to label is always logically true as the same address jump is all of those. That was when the jump to label instruction is executed, the outputs of the jump rungs remain in their last state. That's what we talked about quite a bit last time, is you get in a problem with the retentive nature of unscheduling something or jumping it. How are the input output modules controlled by the master control relay? Yes, it is. The start stop buttons, main disconnect, all of the above, yes. The JSR instruction tells the processor to jump from the main program to a subroutine. The forcing function allows you to turn something on regardless of its actual status. JSR goes false to true, they're in their last state. And these questions, the quizzes were very good on these. Now, to make the connections for the following safety circuit, and so, you know, people were writing this up, and just, you know, a quick hitter on this, just because remember that when you want your safeties, there's two channels, there's S11 here. So you're probably putting, you know, an E-stop, and then it said, you know, use one of the safety gates here, which, you know, you could do 11 and 12 there. And then you could use, maybe it had to be locked. So you're using 21 and 22 here. It'd be open, sorry. And then, you know, it could run whatever. And that's running then, you know, back to here. And then this channel is going to have the same duplicate set of contacts running through here, you know, back to there. So all these contacts just become redundant, and how you pass them through all these safety devices can be, there's a lot of options, okay? But I think everybody's feeling pretty good that you can pass, you know, multiple E-stops, two E-stops, another E-stop, another stop, safety relay, safety gates, whatever, okay? It said this thing wanted to be monitored. So on my monitoring down here, I need something monitoring it. And it said, what was it? The PLC will turn agreement. Have the safety relay monitor the solenoid. So it looks like I'm monitoring the solenoid right here, 33 and 34 of this, to be sure that that's my reset. Or it says, have the system automatically reset once the gate is closed. So I can come right here, and my reset is right there. So it's going to be, you know, my 30 and my 33 and 34 here of when this closes, that resets the safety gate. You know, stuff like that, you know, things like that. So a lot of different ways here. It said that you turn it on the solenoid. So this output right here, you know, runs that solenoid. Keys install the solenoid. The key is install. The emergency stop is key is install the solenoid. So somehow I needed an input here running to the input there. I mean, there's just a lot of different ways that you could set this up to have the relay monitor this and have the PLC monitoring the safety relay through these contacts, and then finally, I think we got a pretty good idea of the safety contact side of this. Let's just be sure. These babies right here, this 2-channel here, this is safety 1 and safety 2. A scale of 1 to 10, am I correct that you have a pretty good idea here of the redundant contacts that need to run into here? Right? Okay. And then, you know, the monitoring here, this could be monitoring the safety situation of the device. A lot of times it's a safety contactor, and then the reset. So these two functions here, you're monitoring your devices, and this could be a big series thing too. This could be a bunch of closed contacts in series. So you got a bunch of gates and motors and starters and everything coming back to here. In this reset, a lot of times it's a push button, but you could have shutting the gate, resetting it, or resetting something resets it. So these two sets of contacts, how are you feeling about resetting it and monitoring it? Very similar, kind of, aren't they? But they're different. One's open closed. One is open closing, and the other one is looking for it to be closed, but they're almost the same thing. And then finally, these are the big kids here. That this is passing voltage here to whatever we're trying to turn on. If it's a contactor or something like that, or the PLC module or whatever, that's the device. And in this case, it was a motor. So, we were turning on a motor like this with K1. If you want to be doubly redundant, I'm sorry, you could have turned on another one in parallel, or you could have passed the voltage here for K2 and put in another set of contacts here, K2. So once again, and these are the big contacts that have nothing to do with any of this. These are doing all the hard work. These are shutting down. Can you use Y1 and 2 from the overload? So I guess you could. You're basically saying, don't turn this on unless the overload is reset. But if I was going to use the overload here for Y2 and Y1, you could use the overload and you could use the K1 contacts in series. So basically that's saying that the starter is off, somehow it didn't get burned on or anything like that, and the overload isn't reset. So yeah, that's monitoring it. That works. Something like that would work for me. You can get crazy. But what do you want in series there to be sure that everything is in the state that you want it to be in, okay? And so once again, the final thing is, everybody, scale of 1 to 10, everybody understands that these are the contacts. These are the good ones that are shutting down the field device directly killing voltage to the field device. No hocus pocus fictional PLC logic turning it off. These are turning it off. Okay, so we've done a lot on safety relays. I really think that we're looking pretty good on them. All right. Lab notes, and I said this was going to be a short lecture, so we've been at it almost an hour. You just want me to finish this up real quick, or does anybody need a break? I think we got about 5 more minutes here. Is that all right if we just pound this out? Okay. And then you got a quiz. You need safety glasses. We're using 208 3-phase, so you're going to be careful. So you can go in the lab tomorrow, but you can't use the 3-phase or set the trainer up. So you'd be making a lot of motor connections. This is all in the lab. You should read it ahead of time just to really kind of review your 131 motor connection diagrams to know what's going on. We're using the DC input modules, and it says it needs a map of your IO. So here's what we end up with. So here's the lab, and this, you're like, oh yeah, this, I don't need to do this, Sean. First of all, at the end of the lab is this thing here. This is like your trainer, right? There's your digital inputs and digital outputs. So you're going to want to label like start, stop, whatever this is. You're going to want to label this because there is a bunch of crazy IO that you're using on this, and you better have this thing right in front of you so that when I say this, can you show me what's going on? So that's what that is going to be, okay? When we come up here, here's what I'm talking about. If you just read every word of this, because it shows you a little grinder, and this is move right, move left. Okay, so without seeing the grinder motor, I'm gonna kind of draw it here. I'm a really good artist here. So here's the motor, and here is the shaft of the motor, and it's got a screw item on here, and then it's got a table on here through the gear here that moves back and forth. Okay, and so there's a limit switch here, limit switch, and there's a limit switch here, limit switch. Okay, so this thing moves back and forth on the limit switches. Okay, this is my little description here. Makes sense? Does it seem like it's making sense how this is going to work? And then this table will hit the limit switch. Okay, and this table will hit the limit switch. Okay, so what is this a program for panel building? It's no. It's a lot more. It's a lot more to it. So it's the trainer that you use for panel building. So when you do this, what you have to do is you have to decide what is the direction of the motor to get you to move right and move left. And remember, if it's not working like you want it to, you could always switch one of the 3-phase leads coming in, directly out of the disconnect, and then everything runs backward the other way, right? Seems like stamping in PLC1. Yeah, this is gonna be a lot. Yeah, it has components of that. So figure out the motor direction to move right and to move left. Okay, and so when this thing starts, when you first hit it, it always moves this way towards the motor. So when you start laying this out, is that move right or move left? I don't know. It's whatever you set it up, but you have to understand that it's moving right or moving left, and move right, move left. So I don't know. You got to make this. You got to, as you face the motor shaft, motor turns clockwise to go right, motor turns counterclockwise to go left. So you have to be sure it's running like that if that's what you're using, and identifying the left limit switch and the right limit switch. Okay, so you're like, this doesn't seem like a big deal, Sean. It does, because people program this all up, and then they program it with the right limit switch instead of the left limit switch, and they got it backwards. And they'll scratch their head for like an hour trying to figure out how this works. Read these instructions, okay? When you get your item hooked up and your three-phase all hooked up, take the contactor. This contactor, yeah, here's the contactor. Take the contactor, take your pencil, and push down on the contactor and see which way it goes, okay? And see clockwise, is it going clockwise? It's going the wrong direction. Switch through, you got to switch some leads, or you got to wire something up so that when you push the forward and the reversing motor starter, it's going the direction that you want, or you're gonna struggle. All right. So read all this, and then here is some ladder logic. Study the circuit so that you understand the forward and reversing functions while holding contact 1 RSS. You better study this a lot to be sure that you understand what this is doing based on there. But it doesn't work. It says the program's generic on the previous page, and this is where you run into problems of trying to convert something from PLC or from hardwire to ladder. It starts having you go through this and add things, and it tells you what all these things are. You're going to create your tags, you're going to create your IO, get your addresses set up, your push buttons, how you modify the circuit. You got to read this super carefully and do exactly like it says to put into a master control circuit. Okay, and so if you go through all this and you do it, it just runs perfectly in like an hour, and you're going to be in business. But if you miss something, you don't know which way is left and which way is right, and which limit switch is open and closed, and whatever, it's gonna hurt. All right, I'm just giving you a heads up. But you're going to see some really crazy things trying to get this to work like you think it should work. And it starts with understanding what they're trying to get you to do right here on this ladder logic. And then you'll be like, why doesn't it work? You're going to figure it out. And then after that, it goes cycle control. Once you got that, we put some stuff on here for pilot lights, and we put in some jog control, and finally we put a safety relay on it. But the main thing is, if you can get this thing running, part A, pretty quickly, based on your connections here, goes over this and that then it goes okay. So I would read this and be prepared. And so you'll kind of be programming, and when you start arriving to the lab, once again, I'll try and get there. Well, I'm gonna have a hard time getting there by about 4:15, 4:30. I don't know when I get there, but I'll get there, and then I'll start pulling the trainers out. But you can kind of start programming it step by step on part A. All right. So that is the lab. All right. So that's, like I said, it's going to be kind of a short one because I've been hitting you pretty hard. I'm going to give you a little bit of a break here. The quiz is a quick hitter. It's 15 minutes, just over some of the basics of networking right out of the book that you learned. So take it easy on you a little bit. I'm going to stop recording, and I'll check this. What questions can I answer?
So, on homework 5, I kind of feel dumb asking this, but the first ladder has a timer relay, and
Okay.
then it also has an output called T. Is that a different timer relay? I've never seen output T before.
T, that's a timed relay.
Okay, so there's just two different timer relays in that?
That's for the delta Y.
Yes, I believe so.
Yeah. So basically, you're bringing in the two contactors, right? One is to start at a certain time, and the other one is to switch the leads for delta to Y, and they just want to be sure that there is a differentiated time before those connections are made, so you don't get a dead short. You know what I mean?
Yep.
Okay, good. And then those that have 232, that will look familiar. All right, what else? Okay, there's nothing else. It's a quick quiz, and be a very exciting lab. I hope you can go go take your quiz. Pretty easy one tonight.